Hello grade 11 students. Today we start with a new unit, electricity. In this unit we cover two chapters for this year, the electric field and capacitors. Now the electric field is of minor importance for grade 11. However, it's a good introduction into the field theory. Before we start with the electric field, we're going to go over the field theory in general and apply it to gravitational fields. Then we go into studying the electric field with some details. So let's get started. What comes to your mind when you hear the term fields? Is it possibly a field of wheat grains? Or is it simply a football field where we go and enjoy a football game? Well, it's neither. However, there is something common between what we have seen here. A field is a region of influence of a certain element. So if you apply that to the field of the wheat grains, or if you apply it to the football field, you notice that there is a certain element common for both. In physics, fields are either scalars or vectors. They are scalars when we just need the values and the distribution of values. They are vectors when the values account along with the direction. A good example on scalar fields is the temperature distribution. If you look at the figure to the lower left, which shows the average annual temperature around the world, you can notice that the values of the temperature or the ranges of temperatures are indicated by colors. On the upper right side, there is something similar to it, which is the temperature in Denmark as given by a weather forecast for a certain day. In both figures, the distribution deals only with values, no need to specify any direction. That's where the term scalar comes from. On the other hand, vector fields require two things, values and directions. Some examples on vector fields are the magnetic fields and the electric fields. If you look at the figure to the left, it shows the influence of a charge, which is known as electric field, and this is the subject of our chapter. The figure to the right shows the influence of a magnet on the region surrounding it. You notice the lines going out of the north and coming into the south. We might study magnetic fields later on during this year, but the influence of a magnet on a region surrounding it is known as the magnetic field. The third example is gravitational field, which is the region of influence of a certain mass. Gravitational field is also a vector field, but it has one direction. And we're going to talk about this in more details right now. Since mass is always positive, then the gravitational field has one type or one nature. If you look at the figure to the right, you can see the mass surrounded by these virtual lines, which are directed down inwards. So the field lines produced by this mass are directed into the mass. You can observe the vector orientations. By convention, the field lines are considered radial and into the mass. Now, why do we study the gravitational field? First, we are all familiar with the gravitational field, with what we call as gravity in grade 8 and grade 9. And using the field theory here, applying it, is going to be a little bit less strange for us. Isaac Newton proposed an explanation for gravity and for what holds planets together. According to Newton's theory, the gravitational field Gm of a certain mass is given by the equation G, a constant, multiplied by the mass itself, divided by the distance squared, the distance from the point we are studying in the first place. And he added UR, which shows the radial orientation of the field. The constant G, 6.67, is known as the universal gravitational constant. It is expressed in SI units, regardless of what these units are. According to Isaac Newton, the same interaction that holds Earth to an apple is the same interaction that holds Earth to the Moon. Now, how to explain that? He went to the field theory. So starting from the equation that Isaac Newton suggested, which includes this G, this weird value, the empirical value, which Isaac Newton suggested experimentally. What's interesting in this equation is that at the same time Isaac Newton was demonstrating it, another English scientist by the name Cavendish was also studying gravitation interaction, and he came up with the same empirical constant. If you look at the figure to the right side, you can see Earth, a huge mass, surrounded by these virtual lines coming into Earth, and these concentric circles. These circles show regions of uniform, or not uniform, showing regions of constant gravitational intensity. Since the mass is positive, as we said, the field lines are directed in one orientation, which is into the mass. That direction is the radial, or what we have studied in kinematics as the normal direction. If you remember in chapter 4 kinematics, when we studied the normal and tangential axes in Frenet reference, so the radial is the same as the normal direction that we have considered back then. Now we go over an application to check what does gravitational field mean and link it to our daily life and what we know so far. The mass of Earth is around 6 times 10 to the power 24 kilograms, and its average radius is 6,400 kilometers. The gravitational constant is also given. The first question, calculate the intensity of a gravitational field on the surface of Earth. In the second part, how much does this field become at the level of the Moon, which is 384,000 kilometers away from Earth? Going to the solution. First, we start by the equation, G equal Gm over r squared. You notice that we have eliminated the vector. There is no vector here. Okay? Why is that? Because we just need to worry about the calculation. So we erase that. Now, we go towards to the radius. R is 6,400 kilometers. We convert that to meters by multiplying by 1,000. Replacing in the equation, thus we get 9.77. and Newton per kilogram. Now, why Newton per kilogram? We'll come to that later. Okay? But the 9.77 reminds us of the value 9.8. So if you go back to grade 8 or grade 9, when we studied weight, we said weight is the force of gravity, and weight equals m times g. What is that g? We called it back then gravity constant or gravitational acceleration. It's nothing but the intensity of the gravitational field suggested by Isaac Newton. And this calculation shows it. If we continue to part 2, in which we calculate the gravity on the gravitational field on the level of the Moon, first we convert the radius from kilometers to meters, replace in the equation to get G equals 0.0027 Newton per kilogram. Pretty small value. However, if you multiply this in the equation of W equal m times g by the mass of the Moon, it's going to yield a huge value of force, which is the force that's pulling Moon towards Earth. We're not going to rush things up, okay? Now, we didn't talk about forces yet. Right now, we're studying the fields, okay? Now, in the upcoming step, we will go to the force and relate forces to fields. At the end, these fields explain the field forces like gravitational force or magnetic force, but this will be in the upcoming section. Before we do that, I would like to go to another explanation of the gravitational field. The gravitational field as proposed by Isaac Newton has a small problem. It has this value g, which equals 6.67 times 10 to the minus 11. Where does that value come from? According to Isaac Newton, it's empirical. It is experimental. A scientist didn't accept that. After 300 years of what Isaac Newton suggested, Albert Einstein, a German-American scientist, wanted to explain the origins of gravitational fields. So he started a theory called the General Theory of Relativity, in which he explained it using the fabric space-time. If you look at the figure to the right side, you notice this black sheet, or this black cloth. It is the fabric of space-time. When you place a certain mass, such as Earth, it is bent. This curvature produced by a certain mass is what we interpret as the gravity or gravitational field of this mass. This is how Albert Einstein was able to explain the origins of gravitational field. It is not as simple as we can see it here. It is a pure mathematical development and explanation. Anyone who's interested can go over the internet, type in GTR or General Theory of Relativity, and you will have tons of explanations regarding it. We are just mentioning it here just to have another idea about how are fields explained in different terms. From Albert Einstein's perspective, this is how space looks like. Each of these two objects, which are Earth and the Moon, produces its own curvature in the space-time fabric, and thus produces its own gravitational field or gravitational region. Now we notice that due to the smaller mass of the Moon, it has less gravitational curvature or gravitational field. Anyway, as we said before, if you're interested in this, you can go and read about it over the net. Right now, we will continue with the field theory, in which we study the interaction between objects. So if a certain object produced a field, how will that field affect nearby objects? Let's go to study gravitational force. So we start with the gravitational force. When another mass comes into the region of a gravitational field, a force is produced. So mass capital M produces a gravitational field around itself. When you place another test mass into that region, it will experience a force. Mass M produces these field lines, and when you place another test mass here, it will experience a force. Now how can we calculate that force? It's simply given by the equation. Gravitational force equals mass times gravity produced by the capital M. So small m is the test mass, capital M is the mass that produced the field in the first place. I'm going to erase these just to keep it neat. Fg is the force exerted by capital M on small m. By this, we were able to explain the origin of the field force, which is known as gravitational force. Okay, right now, after covering gravitational field and the gravitational force resulting from it, we are good to go and start with the electric field. What we have studied is for general information. I don't want you to focus on them, but keep them in mind when we step into the world of electricity and electrical charges, because electricity is a bit vague for us. So let's get started.